Hello everyone, you are welcome to clip 3 of part 7, which is related to the wide area network and mainly about cellular networks. We have already discussed in the previous clip about the GSM network, and also we introduced the 3G cellular network, which is known as the UMTS. Um, as we mentioned before, that the second generation was quite limited due to the radio interface. It was based on a frequency division multiple access and time division multiple access, and every channel was only 200 kilohertz, and every channel is divided to 8 time slots. And even if we use all 8 time slots, still it is very limited to be used for high data rate. However, as we mentioned, also GSM was working fine for its purpose, because the purpose of GSM was for voice communication and like small data rate communication, like messaging, SMS message, for example. And for that purpose, it was very good. However, that of course we included also or introduced also the packet switching to GSM under the GPRS, and also the data rate was increased with the enhanced edge, which was very good at that time. It was possible to achieve about 400 kilobit per second. In 3G, the first thing that we to get rid of is the limited bandwidth. Because of that, they use in 3G 5 megahertz bandwidth for each channel, and in that sense, we have like plenty of available bandwidth that we can use. However, of course, for this 5 megahertz, if you remember that we said 200 kilohertz in JSM per channel, and then 8 time slots, and then we can use many carriers. And now we have 5 megahertz available bandwidth, and then we can divide them among users by using direct sequence code division multiple access. So by using like orthogonal or close to be orthogonal code the division multiple access, that it is called direct sequence split spectrum, as we have already discussed them in the previous parts. In that sense, we are able, of course, to use the or to distribute this 5 megahertz over like many users. For example, if each user we want to allocate, let's say, 1 megahertz, then of course we need to use just theoretically, of course, like 5 orthogonal codes, and then we can use in that sense the coding or the splitting factor will be 5. Okay. And with the 3G, actually it was possible to achieve about 42 megabit per second. This is of course by cell or per sector actually. And if we go to by user data rate, actually it was much less than this one. So the actual throughput per user in the 3G was around 3 megabit per second. Of course, it is much larger than the what we can get in the JSM. However, of course, it is not enough if we want to watch, for example, high definition video. This is the reason that we go after that to the 4G, as we will see later. So in 3G with release 7, it supports also the 64 QAM and MIMO 2x2 MIMO to increase the data rate. So here we can see some like comparison between the wide band CDMA with high speed packet access and the JSM with edge. So we can see some like comparison, like the carrier spacing is 200 kilohertz in the JSM, but here we have 5 megahertz. The frequency reuse factor can be between 1 up to 18. Here we have 1, but of course we have multiple carriers, so we can use also different carriers. However, that the orthogonality is achieved by code, not by frequency. So we don't need by default to use the same to use the frequency reuse factor or the frequency reuse distance, because otherwise we will have interference in the JSM. But here the base stations and the users are separated by using orthogonal codes. The frequency diversity is 5 megahertz and also using a RIC receiver. In JSM, we use frequency hopping and also frequency diversity. Power control, we need actually power control in case of multi-user communication in direct sequence CDMA, because the codes cannot be orthogonal 100%. Because of that, we will have some interference between them. So in that sense, we will need to use power control to reduce the transmitting power for those close or closer to the base station than for the others that they are far away, as we will explain later. So that because of that, for the CDMA, actually the power control is needed at 1500 hertz, means that the power update for the in the uplink and downlink can be up to 1500 times per second. So all the time we need to transmit just the required power to achieve the quality of service. In JSM, because of the interference is not directly dependent on the to the interference or to the adjacent channel interference. So because of that, only 2 hertz or 2 times per second is enough, and sometimes it can be once per second. So the purpose for the JSM is mainly to reduce any unnecessary power. Okay, because always it is good to use small power for the mobile phone, for example. Quality control, as we actually explained in the CDMA, we can control the quality by using for example, the spreading factor or the processing gain in the direct sequence CDMA. So we can have like multiple, we can increase the cell, the number of users. It depends on how the spreading factor, for example. But in the JSM, it depends on the network planning. In the downlink modulation, in the white CDMA, we can use quadrilateral phase shift keying, 16 QAM, 64 QAM in the high speed packet access relay 7. And in the fourth generation, of course, we go to the OFDM. But in JSM, we use the Gaussian minimum shift keying, which is actually one kind of binary phase shift keying, and 8 phase shift keying for the edge. So this is just fast comparison. Before I go to the next slide, I just want to mention a little bit about this power control. Assume here that we have this base station, okay, and now we are in the downward link. So we have one mobile very close to the base station and one mobile very far. So this is mobile A and this is mobile B. Okay, so now for mobile A, that we will need to transmit with power P1 and mobile B with power P2. Okay, so actually because that for mobile B2, because the mobile B2 is far away from the base station, and if we want to achieve the same signal to noise ratio at each mobile, then we should use higher power B2 than power B1 to achieve. Um, Actually, I don't know if we can call it fair or not fair, because we will define it in different way, the fairness later on. But now we need to use much higher power for those which has like far away. But as we increase the power for B2, then the interference for mobile A1 will also increase, because as I said, we cannot get like 100% orthogonal spreading factor or spreading code. Because of that, the high power for user B will increase the interference for user A. By the way, I would like also to mention one important thing, that the bad or good channel, it is not necessarily related only to the distance, because of the deep fading or because destructive fading, it can also that it can make such kind of behavior that the closed mobile might also have very small, like, or very high attenuation, not because of the distance but because of the destructive fading. Okay, so we need actually the bulk control to be fast enough to substitute also the fading which can happen to the channel. Okay, and how to handle this problem? Actually, one method is using the by using the scheduling. So the scheduling idea is that uh, if we select the best mobile, for example, mobile A1 or mobile A or mobile B at a time, and instead of distributing the power among them, then if we use all power for only A, so now we put this is zero, and we put the total power, all the power is for A. When we use the whole power for A, what happened? The EB over N0 will be very high, and because of that, of course, we can also reduce the processing gain. Reducing processing gain means that we send more data for user A, and also we can use higher modulation level, for example, using 64 QAM instead of binary phase shift keying, or instead of quadrature phase shift keying. In that case, we can deliver very high data rate for user A. Okay, and after that, when we serve user A, we can switch to serve user B, and also we can allocate all the resources to user B at good time. So this is called like opportunistic scheduling, that we select the mobile phone which has like good channel quality, and we give the whole resources to that mobile. But this scheduling, it might introduce some like non-continuity in the data delivery. So it is excellent for internet exploring, for example, or for data, or for uploading or downloading files. But if you want to have like high quality and or very small latency, like for voice communication, so this scheduling should be done very carefully to guarantee that, the latency or the delay is not exceeding some like a maximum allowed delay, for example 500 millisecond, half a second, or zero point 0.3 second. It depends on the quality required. Actually, in JSM, the delay was around 60 millisecond, so it was a very small delay for the voice communication. But here, to get higher performance in the terms of data rate and terms of a quality of the voice, we might increase this delay somehow. Okay, and in a 3G network, we can see that it consists of three levels: the user equipment level, where we have the air interface with UU interface, which based on the CDMA, white CDMA. Then we have the UMTS terrestrial radio access network. So this is the hub, as we have seen already in the radio hub, as we have seen in JSM, and then we have the core network. Okay, um, actually, I don't want to spend very long time explaining the structure of the mobile phones, but I will just go very briefly. Here you can see that the integration between JSM and 3G. So this is for JSM, and this is for the 3G network. So you can see here that in JSM we have the base station, or the base substation that we explained in clip 1, and then we have the base transceivers. As you can see, they are connected, of course, to the mobile phone, and then we have the ABIS interface with the base station controller, and then the base station controller is connected to the mobile switching center, or it can be connected to the serving GPRS support node, which the added item to the GPRS to deliver or to deal with the packet switching for the internet or for the data communication. So this is in the JSM, but now this is in 3G. So you can see that we want to keep the compatibility between 3G and also the JSM. Because of that, actually, many of the items of the network here, it was being, or it has been also used for the 3G. So in the 3G network, actually we have some changes in the name, like here we have like radio network station or substation, and here we have also where here we have the node B. Instead of using base transceiver, we use here node B. And then we have, instead of base station controller, we have radio network controller here. But actually the concept is still the same. So the radio network controller, it takes care about the handover, about a lot of uh, coding, encoding, and mini control of process of these node Bs or the base stations. We have something new here. We have there is a connection between radio network controller and another radio network controller inside the same public LAN mobile network. And this actually this increase, or this connection, it provides the feasibility of using soft handover, as we will see them later. And then of course it is connected to the mobile phone through the air interface, which is based on CDMA, wideband CDMA. And now we have the RNC is also connected to the mobile switching center by the interface IU, interface U, circuit switching, and also it is connected to the serving GPRS support node through the interface IU, the packet switching. And you can see it is the same here. And we can use the same, actually, home location register. It is used the same for JSM and also for the 3G. The equipment identity register also is used for the same networks. And then we have the gateway mobile switching center, which is connected to the other like circuit switching network. And then we have the gateway GPRS support node, which is connected to other packet switching or packet data networks. Packet data networks. And also we have the, for the mobile switching center, we have the visitor location register, and they are the same, actually used for the both network. But remember that even we use the same equipment, at least by names, but actually in order to make the mobile switching center and the serving GPRS support node to be compatible also with the 3G, several upgrading has like had been done for both, actually, to be compatible also with the 3G. So it is not just directly connecting the new network or the new standard with the previous items, but the previous items, they went also through some like hardware and software upgrading in order to be compatible with the new requirements. So this is simply that, and briefly, the connection of 3G network with the JSM network. Okay. Uh, Actually, what was the problem here? If we look here, we had two major problems in this 3G and also in the JSM. The first problem, that the complexity of the radio network substation, the radio network substation, or as it is called, the terrestrial radio access network, terrestrial radio access network. Actually, it has controller and it has the base station. So many functions that should be done that at the radio network controller. For example, if we want, or there is some handover during the mobile or the device that they need to hand off from one mobile to another mobile, they should request this from the radio network controller, and the radio network controller start to have established a connection to the device, and then they start the process from the radio network controller by informing the base station what to do and what to shouldn't do, and so on. So there is a lot of communication between the mobile phone or the user equipment to the base station, from the base station to the radio network controller, from the radio network controller or the base station controller to the to the base station again. Sometimes the radio network controller needs to take like commands, or it takes the permission to do some action from the serving GPL support node. So they need also to communicate with the serving GPL support node, or communicating with the mobile switching center, then waiting for the permission, and then go back. So a lot of protocols, a lot of exchanging of data, which sometimes reduce the efficiency and introduce a lot of latency, a lot of delay, unnecessarily delay. So those was that one limitation in the 3G and also in the GSM, which we are going to see how to be handled in the 4G. The other problem is here the mobile switching center and the circuit switching in general. So the circuit switching, even it can like provide high reliability, but in the same time it is not efficient in terms of like size, required size, consuming power, cost. Also, in case that of having a lot of devices, there are a lot of limitations actually with circuit switching. With circuit switching, we have a lot of limitations, and it was very important step to get rid of this circuit switching concept. So and everything should be based on IP or Internet Protocol, or it is sometimes called connectionless procedure. Okay, and so this is actually in the 4G we start to have the all IP core network. Okay, what is the radio part in UMTS? As we mentioned before, that the radio part is based on CDMA, and in UMTS standard they use uplink from 1885 up to 2025 megahertz. So the total is here 15 and 25, it is 40 megahertz for the for the downlink, for the uplink, and for the downlink is from 2110 up to 2020 megahertz. So we have, this is for the uplink and also for the downlink. Also there are some other bands available for different countries, and actually it was also using some bands from 900 megahertz. There were some band was like allocated also to be used for GSM, but that band also later it was used by UMTS as well. The idea of modulation, as we said, that it is based on the spreading or the multiplication in the spreading code. Actually, we have two spreading codes in JSM, sorry, in UMTS. One is called channelization code, and then we have scrambling code. The processing gain or the spreading factor is done actually in the channelization code. So we have data here, and then we have the chip rate and the output. But in the scrambling code are actually, they don't change the data rate or the chip rate. So the chip rate is the same, which is in UMTS is 3.84 mega chip per second. So it is the same, but still we multiply it with the scrambling code, which gives the orthogonality. So the orthogonality between users are given here. The orthogonality between base stations also is given here. Okay, what is the orthogonality here? The channelization code is used for the orthogonality between the same user inside the same cell, so or the same base station. So the base station or the node B, when they send in the downlink, they use scrambling code, which identify this base station, but the users inside, so they are like they are separated by using the channelization code. Okay, so in case, for example, in the codes we might have the spreading factor of 4 or 8 or 16 or 32 and 64 and so on. Okay, so for example, if we have 16, if we use spreading code of 16, it means that if we keep one for for a control message, because remember that we need also control messaging between the base station and the mobile phones. So if we keep one for control messaging, then we have available 15 different channel. So 15 different channel can be used, which means that 15 users, so we can support 15 users in the same time in that case. Okay, what will be the data rate for each user? Because we know that the chip rate is 384, so the bit rate, will be 3.84 times 10 of the power 6 mega divided by 16. So you can calculate the data rate in that case, if we use, of course, the binary phase shift keying. But if we use, of course, like 16 QAM or 64 QAM, then we can calculate the achieved data rate per user. Okay, what is the maximum that we can achieve for one user if we use all these 15 available codes for only one user? Then this user, we will get the whole available resources from that base station. So this is the idea of high-speed packet access, but in that case we need to use scheduling, because we need also to serve other users. It is not fair to you serve only one user at a time, or only one user per sector. Okay. This is the data, how it is divided into the by the in the UMTS. So you can see that we have data. So the data contains about 2,560 chips, because this is by the data or time slot. Okay, per time slot. So we have 15 time slots by time frame. So the time frame is 10 millisecond, and we have those time slots. We have 15 time slots, so you can calculate that each time slot will be 10 millisecond divided by 15, so that each time slot is 0.667 millisecond. In each time slot, the data consisting of 2560 chips. Of course, you can calculate this simply by multiplying the chip rate 3.84 times 10 of the power 6 chips per second times the available time 0.667 millisecond. Then you will get this 2560 chips within one time slot. This is for data. And also we sent in the quadrature channel, we sent also the control information. The control information consisting of the pilot data. Pilot data is some known data bits known for the receiver, and it is used to adapt the equalizer of the mobile phone, and to also to improve the quality of the receiver. It is used to send this data, or it is used to know the channel parameters. Then we have the transport format combination indicator. We have the FPI is the feedback information about the channel quality. We have the TBC, the transmit power control, which is used to ask the mobile to increase the power by 1 dB or decrease the power by 1 dB in the uplink and also in the downlink. So you can see that we sent the information about the TBC, about the update of the power, that every time slot, which means that every 0.667 millisecond, we should send one information about adapt the power, either increase the power or decrease the power. And if you divide this one, divide by 667 millisecond, this gives you 1500 times. As we mentioned, that this is what we need to adapt the power of the mobile phone or of the base station. And the transport format combination indicator, actually, it contains information about the spreading factor used, about the information. Otherwise, if you lost the transport format combination indicator, for example, we will not know what is the spreading factor. So what code that we should use to disparate this information. So this is very important also to be known at the receiver. So how to make the radio resource management in JSM using bar control in the uplink and downlink, rate allocation, handover. We have hard handover like in JSM, but here we have also soft handover and softer handover. We have admission control, we have load and congestion control, we have packet scheduling as in the high speed packet access. So as you can see here, that the quality of the signal depends on the transmission of users, and you can see here that the EB over N0 for user I is the chip rate. This one is fixed 3.84 mega chip per second, and then this FBI can be varied, that increased or decreased. If you increase them, then the processing gain will decrease, and in that case the quality or the EB over N0 will be also decreased. And actually we should use high bit rate only in case that the SNR, this is the SNR, is high. So that if the interference is very small, or if we use some kind of like interference cancellation, so that EB over N0 it can achieve the target, then we can increase the bit rate. Otherwise, if the interference is very high, we have to decrease the bit rate in order to get reliable communication. The soft handover, one of the major drawbacks of JSM, that the users on the between cells, they got the worst service, and now this problem has been handled in UMTS, that for this user who which is in the edge between like two base stations, then it is possible to provide service by both base stations. So in that case, because the signal to noise ratio from this base station will be very small, the signal to noise ratio from that base station can be also very small. But in that case, we can, by using the maximum ratio combining, the MRC, that we can combine both quality signals in order to improve the quality of the user in the edge between two cells. And it is called soft handover. And also the softer handover, because in each cell actually can be divided into several sectors, usually three sectors: one sector, second sector, and three sector, in order to increase the capacity. So it is the same case that when the user comes between two in the edge in between two sectors, then it can be provided from both sectors in order to increase the quality of the signal of that user. This is called softer handover in the 3G network. The high-speed packet access plus, actually we by utilizing the higher modulation, using MIMO, and also by using the concept of opportunistic scheduling, we were able to achieve very high data rate, reached to 42 megabit per second. And the concept, by the way, it is important to mention one thing here, that in my opinion, the most technologies has been achieved in the 4G. If we compare between 3G to between JSM to 3G, there is some achievement, some development, like that, mainly in the usage of a wideband frequency, like this YCDMA, and also by improving the packet switching. But if you look to the 4G, actually the many technologies has been involved in the 4G. However, the concept came also from the 3G as well. So for example, this using opportunistic scheduling, it has been applied much more efficiently in 4G network. So here we use the adaptive modulation and coding scheme, as you can see. So that I can show this one, for example. So you can see this is the received signal quality. You can consider it, for example, as signal to noise ratio, or EB over N0. So now we have three users. So because of this fading and the random fading, you can see that in this part, that the brown user one is the best. So now we serve user one. Here we have read the user 2 is the best, so we serve user 2. Here we can serve user 3, user 1 again, user 3, and so on. So this can work in case that we have like uniform distribution of the fading among all users. But this is not happen in reality. So in that case, we can use some kind of algorithms that taking into account the service that it was given already to the user. So this one is taken into account in order to select which user or that should be served in the next time. Okay, so we can come to this maybe later. So, but this is for the 3G network. For the 4G network, maybe we have already now about 30 minutes. So let us go to the 4G network in the next clip. Thanks a lot and see you.